All right, folks. Today I want to talk a bit about the Mandelbrot set. So this is kind of a hopefully a fun sort of mathematical thing that we can do and use a little bit of the sort of JavaFX stuff, specifically the image tools things that we used on the image processing stuff, and a little bit of math, a couple of loops, and in the end we'll generate this Mandelbrot set, this picture that I have here. So many of you have probably seen this before. It's a fractal. You know, if you start sort of zooming in on it, it's going to sort of look the same as this, but this is sort of the standard sort of version here. We see sort of the big sort of turtle-shaped body here, and then if you sort of look closer, you see little sort of turtle-shaped bodies sort of around this and in different areas. And in principle, we could do like a zooming thing if we wanted to have it be a bit more interactive. But mainly today, I just want to talk a little bit about the math, and then we will code it up. So there's two pieces that you're going to need to do some of the coding for this. I have just a basic class here that contains main, but all of the normal JavaFX stuff is all sort of included here because we'll be using that image tools file that we used before. When we read an image and saved one, we're going to just be saving an image this time. So we're not going to read one in. There's no reason to. We're going to generate this Mandelbrot set ourselves in a 2D array, just like what an image is supposed to be. It'll just be in an integer array. And you'll put a file name in. It'll be our sort of Mandelbrot file name, and then it will write this out. Now, I do have an extra function in here, and it should be in the one that you download as well, that does a sort of color map. So rather than our fractal being just grayscale, which is what we'll start with, I included this color map thing in here. And it's sort of a standard color map, or at least a sort of a good looking color map to use with the Mandelbrot set. So there's a quick change that we would do in this writing file to make it so instead of grayscale, it uses the color map that I created for you guys. So we'll make a quick sort of change to that, and then we'll have sort of a nice looking image. And let me actually bring up, I should have one of these somewhere. I didn't get this ready, but I should have a version of this somewhere so I can show you what that color map one looks like. It's sort of where we're going to be ending up at the end of today. Let's see. This one, maybe. No, not quite. This is still one of the grayscale ones. But one of the things you can see if we sort of zoom in just on the image, this is a very high resolution image. As we zoom in on the image, you start to see a whole bunch of the cool little sort of fractally patterns here coming out of this stuff. So we'll be able to choose a resolution to write this to, and we'll just write a JPEG, so it's not going to be anything fancy, but we'll get a nice sort of colored version of this as well. And I don't remember where I stored that at, but this is the idea of what we're going to create today. And the cool thing is the math isn't that complicated. It's just it's some stuff that you may either have not seen before or may not have seen very much. It uses some sort of complex stuff, but luckily sort of we won't have to worry about it that much. So I head back over to the slides. So this is eventually what we're going to come up with, and we'll have that sort of colored version of this as well. So we're basically going to take a stab at it. We should get all the way to the end. I sort of say here, we may not get to the end, but this being a recording, it should probably be fine. On Blackboard, of course, there's that image tools file. I'll make sure to include that with this set of slides as well, but it should be in the image processing slides as well. We're going to write everything. I say this sort of incomplete Mandelbrot main class, but we're just going to write everything. Just make sure it's a normal sort of JavaFX project, but you don't have to go back to main here. You don't have to extend application. You don't have to have start. You don't have to have any of that. We're not going to have a normal window. The JavaFX stuff is only for writing that image out at the end. So you don't have to do any of the normal JavaFX stuff in the program, but in the setup, you do have to do your normal JavaFX things for your actual sort of project setting stuff. All right, so it's a very easy equation. The Mandelbrot set is not complicated. You could do it with recursion because it's sort of set up that way. But this is it. This is the set to create. This is the equation to create that Mandelbrot set image. That's it. The next z, so z n plus 1, is equal to zn squared plus some constant c that we get to set, and then the first z is 0. That's it. So from sort of an outside view of this equation, it seems pretty simple. But the complication here, and the reason we can make an image out of this single equation, is because these are complex numbers. So for example, c is x0 plus y0. So I here is the complex number. It's represented by the square root of -1. Now, we can't do that on the computer. We can't do this imaginary number stuff here on the computer. So we're going to do some sort of extra stuff to sort of get rid of it, or to sort of just not think about it. The computer, not good at imaginary numbers. It's good at regular numbers, but not imaginary numbers. That means that z here, this z, is also a complex number. So there's two things we need to know. What is c, because that's here on the right-hand side, and what is a complex number squared? So I write that out for you. If z is x plus iy, then z squared is x squared plus I times 2xy minus y squared. So that we have two real parts, and we have an imaginary part. So this is a real part because it doesn't have an I. This is a real part because it doesn't have an I, and this is an imaginary part because it has an I associated with it. This is where the plot comes from. It comes from the fact that we can draw a 2D plane to draw points on, a matrix, using a real axis and an imaginary axis. So I'll show you that coming up here in a second, but just realize that it's just some regular math stuff here. We're just taking x plus iy times x plus iy and using FOIL, using the sort of normal algebra stuff to get to this point. And I'll sort of summarize these equations at the end, and we're going to program something up that does this. All right, yeah, so there's our real part, x squared minus y squared, and our imaginary part, 2xy, with our, of course, our imaginary I here. So that's what we end up with for what z squared actually is. Yeah, so real part, imaginary part. All right, so what we do is we separate them. So the equation that I just showed you, the z of n plus 1 equals z squared n plus c, that is this. But the real part and the imaginary part, right? Because z squared is this for the real, and c, remember c was just x0 plus I y0. So that's our real part for c. And then here is the imaginary part for this equation for z squared, and the imaginary part for c. And we've left off the I. We're just saying, oh yeah, this is the imaginary piece, this is the real piece. That's how we can sort of forget about the square root of -1, the imaginary number. And these are the two equations that we're going to program up. So it's pretty easy. We just need to know an x and a y, and we can code up that original equation, z equals z squared plus c. But we just do it in two equations rather than one, because we have the real part and the imaginary part. Now, typically what you do to get your sort of pixel color, so you saw we had some white pixels, some gray pixels, and a lot of black pixels in the image. Typically what you do is you pick a value of c, and you run that equation. And what you look for is the magnitude of z squared. So this right here. You look for a situation where that is growing, that is getting larger than 4. And we're going to set a few values, things like a maximum number of iterations and all that kind of stuff. But the point is, we keep running that equation as long as this is true. So as long as the magnitude of z squared is less than 4, we keep going with that equation. And I'm going to show you a couple of examples of what happens when we run through that equation. But we just keep going and going and going. And you stop whenever you reach some maximum number of times you run through that equation, which we're going to set. or until Z falls out of this region. That's what we do. We just run that equation, basically this set of equations here. We run those until the magnitude squared is greater than 4. And then we stop. The number of iterations it took, so either reaching n or the number of iterations it took to reach this number, is the color we put in the pixel. I know this might not make a ton of sense until you see an example of it, but in the end, hopefully after we code it up, hopefully you'll be like, oh yeah, that totally makes sense. We just run the equation up to some certain n. If we hit the n or if we go past 4, then we set a pixel color. And that's how you get the image. So here's an example. So let's say we pick a value. We pick a value for C. C is our sort of starting value. Typically, you're going to pick C between -2 and 1 on the real and -1 and 1 on the imaginary. So remember, C is x0 plus I, y0. These are our two coordinates. This is the real axis, and this would be the imaginary axis. That's how we get our sort of two axes to put our pixel on. So typically, you're going to pick between -1 and 1 on the x and -2 and 1 on the x and -1 and 1 on the y. So you're going to pick somewhere in between there for this C. So let's just try C equals 1. So what does that mean? That means that x0 is 1 and y0 is 0. That's it. So if I pick a C of 1, this is what those two values are. So we need to take the first value of Z. Remember that Z0 is just 0. So we start here with 0 squared plus C. Well, C is just 1. So we put a 1 in here and we get a 2. Or we get 1 squared plus, or 0 squared plus 1 equals 1. And then this result goes into the next iteration right here. We're still just adding 1 each time. We're adding C each time because we picked a C. That's sort of a permanent C that we picked for this test. So we do 1 squared plus 1, that gives us a 2. That goes in here. 2 squared plus 1 is 5. 5 squared plus 1 is 26, and so on. So notice if this starts blowing up really fast, these numbers are going to keep getting bigger and bigger and bigger. So this passes that criteria. Remember, our criteria was the magnitude squared of Z being greater than 4. So that basically blows up here in this third iteration. This squared is greater than 4. So it blows up. So I would record, for example, here I would record a number of iterations for this particular test. I would record a number of iterations equal to 3. In grayscale, 3 is nearly black. It's a very dark pixel. So when X is 1, I expect to see a black pixel. Now let me show you on one of the images here. Here's our colored one. It's like it was in the same place. So this will be our colored version that we're going to see later. Let me bring up the black and white one just because that's what I'm sort of thinking of here. So let me bring up that black and white one again. So I said that at 1, I would expect a black pixel. So our window here is exactly what I said in the slide. -2 to 1 on the real and -1 to 1 on the imaginary. So over here on the x-axis, this is, let me just put it here, this is -2 and this is 1. So the point that we just looked at is clear over here because on the y-axis, we've got 1 and -1. So the point that we just looked at is right over here on the edge. It's at 1 on the x, and on the y, it's at 0. So it's halfway in between. And indeed, we do have a dark pixel there. So with this picture in mind, we're going to do one more example. Just try -1. C equals -1. So again, we're still in the middle of the image, because our C here would be -1 plus I times 0, which of course is just 0, so we don't have to worry about it. So we put in the 0 to start with here. We put in -1. We get -1. That -1 goes in here, and I should probably put parentheses here like this because it is doing the square here to get 1. So we get 1 plus -1 is back to 0. Put in 0, get -1, put the -1 in here, go back to 0, and so on. This is going to repeat between -1 and 0 forever. As many iterations as you do, it will never hit that criteria. So what's actually going to happen is it reaches our maximum number of iterations. And we are going to set that. We're going to set n, our maximum number of iterations. We're going to set it to 255. Why? Because this is a white pixel. So this will reach 255 iterations, and then we'll stop because we know that it's just going to keep going forever. So we'll stop. And we'll set that pixel to white. So let's take a look in the image that I showed you. Let's take a look at where is -1 in our image here. So with this guy, remember that our range here in the X is -2 to 1, and then -1 to 1 in the Y. So if we sort of split this here, then like we have like -2, so -1 is about a third between, so -1's about here, maybe 0's about here on the X. So the pixel that we just looked at was 0 on the Y, so it's in the center, and it's here at -1. So that pixel we just looked at is right around this area. And it indeed is a white pixel. So that's all we're doing. We're just running that equation. We're picking a bunch of different values of C. That's the point here. Every single pixel you see in here is a different value of C. So we run potentially millions of different values of C and see what color of pixel they should be. So for every single pixel in our image, that's what we do. We see what the value should be, record it, to translate it into a color. So a low value would be darker color, a higher value would be a lighter color, and then that's it. And then we've got our Mandelbrot set image. There is one more complication to this. And yeah. So some values of C, some that we pick are going to diverge quickly, some slowly, some never at all. So in other words, some will be light, some will be dark, some will be in between. All right, so there is one more complication here. It's plotted on the complex plane, but we have pixels. We have pixel numbers, like maybe up here is like pixel 0, and then pixel 1, and then pixel 2, and pixel 3, and so on. But technically, these are just numbers between our -2 and 1 and our -1 and 1. So we're going to have to translate between a pixel number, like if I look in here, like this pixel number here might be, I don't know, might be 300 and 1500, who knows, whatever sort of pixel I'm located at. But I need to translate this into a number here, which might be something like X, it might be -1, and for Y, it might be like 0.8 or something, or 0.9, whatever. It's going to be some number. This is the X and Y that needs to go into C, not the pixel numbers. We don't want these. These don't go into C. That's not how this is going to work. We need to translate from a pixel number to an actual complex number and then run the calculation. So there is a sort of translation that takes place that I'm going to show you how to do that in just a second. But when you're looking at C, just think X and Y. That's our coordinate. So real axis, imaginary axis. It's just two coordinates to plot an image. That's what's happening here. All right, so like I said, you can visualize the Mandelbrot set or make this image by assigning a color value to the number of iterations it takes to pass that threshold value. Lower number of iterations, darker color. Larger number of iterations, lighter color. That's what our grayscale version is going to look like. And this is what we will make with the code today. In addition to that colorful one, so here's that colorful one, we will make this one as well. And in here, you see a lot of sort of interesting sort of stuff happening as you get sort of as you zoom in sort of more and more. A little bit more interesting than the sort of black and white one. This is sort of a color sort of gradient that really highlights the edges of stuff that's going on here. So this is the sort of color map that I gave you guys in the tools, in the image tools folder, or the image tools file. All right, so here is the sort of summary of the complex equations. To take the magnitude squared, it's just x squared plus y squared. Remember, this is the real part, and this is the imaginary part. Here's those real and imaginary parts that we need for that full equation. The z squared, write that properly here, the z squared plus c, that's this here. And then this is a conversion from pixel space to coordinate space. So I have a little bit more sort of detailed slides on this, but this is a conversion we're going to use in both dimensions. We're going to do it in the x and in the y. So let me give you an example of that. So here's our image. And again, it's just a matrix in pixels. So up here, we might have pixel 0, 0. And then right next to it, we're going to have pixel 1, 0, and so on. But the actual XY values are what we need. And that's the -2 to 1, -1 to 1. So we need that conversion. We need to convert from the pixel we are in to the location in this complex plane, this sort of XY space. So yes, we got our -2 to 1, -1 to 1 for our real and our imaginary. And then, so that means like 0, 0 is like right here. Right? The 0, 0 in the complex plane is right here. But our pixel 0, 0 might be up here in the corner, for instance. Now, to start with sort of a low resolution image, let's say we had 900 by 600. So 900 on the horizontal axis for pixels and 600 on the vertical axis for pixels. So let's say that's our sort of pixel numbers, and this is our real and imaginary numbers. So what we do is we take the range for our x and y. So for x, what's the range? We go from -2 to 1. So the range here would be 3. So notice I take end, that's 1. Draw this out here. That's 1, so that would be the end. And then the -2 would be the start. 1 minus a -2 is 3. So think of this as the range. Same thing here. The range would be 2. We would go from 1 and -1. So for the real, this value is 3. For the imaginary side, this value is 2. We have the start here as well. The start here is -2, and the start here is -1. Think of it as sort of a left to right. So left here is -2. The bottom to top, this would be -1. So it's the same values we used over here. Then we have this little multiplication. This is actually just, you can sort of think of it as like a ratio. It's, we start at -2. How much of the range have we moved in our pixel? So this is going to be our current pixel. I'll use the text thing for this. That's the current pixel we're looking at. So that's the current X pixel, is the current Y pixel. So this is literally, this is what is in our matrix. The num here, this thing, for the X and the Y, this is the total number of pixels in that dimension. So remember, for X, we have 900, and for Y, we had 600. So most of these are just constants, right? It's just -2 to 1, the calculation here, 3 and 2, and then the current pixel that we're looking at divided by the total number of pixels in that dimension. And this gives us the X and Y that then go into C. That's what it gives us. So we're going to code this up. It's relatively easy to do. We're going to have all these values to sort of start with. These will all just be variables, and we're going to have two loops, one over I and one over J, to loop over our entire image. So I and J will literally just be I divided by 900, J divided by 600. The thing to remember here is that we don't want an integer division. We don't want an integer division here, because otherwise this would be 0, because we'd have like 500 divided by 600. That would just be 0. So we do want this to be an actual fraction here. So that's something that we do have to think about. But that's how we go from this sort of pixel space, this pixel number, to the coordinate space that we need to actually run the equation. All right, and I have a couple pop-ups here, just beginning of the axis of the axes. I and J, that's the pixel, and then y num and x num is the size in pixels that we're making our image. And then this is the range in the complex space. So -2 to 1, -1 to 1. So that's the idea of this conversion. All right, so again, for our specific space, it's going to look something like this. So I sort of wrote that out manually, but I do have it on a slide as well. So our specific case, -2 plus 3, this is the 3 here, times I divided by 900 and J divided by 600. So that's how we get our two values. And that's what we will do when we actually code it up. And then, of course, don't do an integer division here, because it'll just be 0. All right, so that's the equations that we need to use. We'll need a few values to a few variables to sort of keep track of stuff, and then a couple of loops. And we'll write out the sort of matrix that we end up with. So this should be just about it for the slides. I do have some pseudocode here, just sort of the general stuff, like decide the image resolution and the max number of iterations, decide the range, so -2 to 1, -1 to 1, loop over all the pixels, convert the pixels to the points, the X and Y points, set C to that point, loop until we reach the max iterations. This will be a while loop. So we're going to have two loops here. So we get all the pixels, and then we'll have one while loop where we actually do the equation. If the Z becomes greater than 4, then we stop and we record, and we restore the iterations. We store the number of iterations it took into our matrix to plot the image. That's it. And then we'll write to the image. So yeah, let's go ahead and code it up. Then we'll write the image, and we can take a look at the colored version and the grayscale version as well. So let's jump in here and actually do it. I know that the math is, there's some complex number stuff, but in the end, it just comes out to be a little bit of algebra and sort of thinking about how we do that pixel sort of conversion thing that I talked about. So let's start on this. So let's just think of the resolution of the image first. So let's see, image resolution. So we'll do a sort of a low resolution first, and then we can increase that if we want some more detail. So I'm going to create an int. I'm going to call it width. And the width, we said 900. And the height, we'll say 600. So that's our resolution. Let's make the matrix to save the image values, so the pixel values. So I'm going to create an integer matrix, and it's two sets of brackets, right? It's going to be a matrix. So it's two-dimensional. I'm going to call it mat, and this will be a new int. And I'm going to use height and width. The reason I'm going to put it as height and width is essentially I is going to be the height, J is going to be the width. It's mainly because of the way that the image tools writes the image out at the end. All right, so now let's make some variables for some, say, like vars for the real and imaginary parts of C and Z. Now, oftentimes I'll use sort of very condensed sort of variables for this, but I'll be a little bit more sort of descriptive here. So I'm going to say I'm going to create a double, because these need to be doubles. These are, these have decimal places with them. So I'm going to make a double here, and I'm going to call it the imag of C. So that's the imaginary part of C. And same thing for the real part of C. So we got the real part of C and the imaginary part of C. Then we have the imaginary part of Z and the real part of Z. So remember, these two values here, these are picked based on the pixel. These ones start at 0 and change every iteration. So that's what these Z's do here. We also need some vars for the start and end of the range. So basically, what is our window going to be? So I'm going to say this is so we'll create doubles for this. So the real start is -2, so that's the left. And actually, let me use the real, this. And the real end is 1. So that's the end of our range. And then for the imaginary, for the start, this is -1. And for the imaginary end, this is just 1. So that's our window. And so I've made these variables so that we can come back later, and if we want to change what the window is looking at, maybe we want to do like a zoomed in view, we can do that. And then lastly, we're going to have the var for the max iterations allowed. And I'm going to pick for this, we're going to have an int max iter, and this is going to be 255 because that's a pure white pixel. 255 is pure white. So that's why I'm going to pick that number. If you wanted to do something, maybe you'd have to do some like mapping stuff, but if you wanted this to be larger, you certainly could. But then you'd sort of map, you'd be like, oh, the largest value that this is would be the pure white pixel, and then anything less would have to be mapped in some other way. So these are the sort of setting up variables we need. We need to know the resolution. We need to actually have the matrix that contains all of those pixels. We need to have some variables for the real and imaginary parts of both C and Z. And then we need to have the starts and the ends of our sort of window that we're going to create, and then the maximum number of iterations that we're going to allow. And this will happen in the while loop, in our while loop. And really, it's just now we just need a couple of loops. There's actually not a whole lot more left. So we're going to loop from I = 0 to I less than the height. And same thing for the j. J = 0, j less than width, j++. So this is the situation where we pick a pixel. This should be very, very familiar if you watched the image processing one. The first thing we do is pick a pixel. So that's the ij pixel that we're picking. So essentially, if we think about it in sort of a picture form here, we've got just an empty image. And our I and j, we're going to pick a pixel. So we're going to pick pixel 0, 0 to start with. And then we're going to keep going. We're going to pick the next pixel, so on. So think of this as the pixel that we're picking. So what's the first thing we do once we pick a pixel? We convert from pixel to the real imaginary plane. So we need to take the pixel number and convert it so that we use the imaginary C and the real C. So we're going to set these two values. So remember what this was. This was the start. So we're going to do imaginary first. So this is the imaginary start. That would be -1 in our case. Plus, I'm going to put parentheses around this. This will be I divided by. So our imaginary, remember, imaginary is the height. So that's I divided by the height. That's the number of pixels that we have. Times, this is our range. So this is imaginary end minus imaginary start. So that's from the slide that we had before. Now, this is going to be an integer division here. Actually, yes, because height is an int and I is an int. So I'm just going to put in a 1.0 times I here so that we don't have that integer division happening. And the real is exactly the same. It's the real start plus 1.0 times, this time it's j divided by the width, times the real end minus the real start. So that converts us from the pixel we've chosen, pixel I and j, to the imaginary part of C and the real part of C. Now, we have the real imaginary part of C. We need to give the initial value. So think of it, so these are the initial value of C, which is constant for each pixel. And then here, next, we're going to do the initial value of Z. So what is Z to start with? It's just 0. So the imaginary part of Z is 0, and the real part of Z is 0. That's based straight out of our equation. And we're going to create one more variable. This is going to be, I'm going to call this iter, and this is iteration 0, because we're going to increase this value every single time we go through the particular while loop. So now is the while iter, the value we just created, while that is less than max iter, then we keep going. So we can do this stuff a maximum of 255 times. Now, I'm going to write this up in it's pretty much the sort of naive way. It's basically the naive way to do it. We're going to take the real part of Z and set that equal to. So if we look back, let's look back at our equations. The real part of Z is equal to the real part of Z squared minus the imaginary part of Z plus the real part of C. So remember that this is the real part of Z, the imaginary part of Z, the real part of C. So this would be, if I say this will be real C. This is real Z. And this is imaginary Z, imaginary part of Z. So that's where these values come from. So that's exactly what I'm going to code up. So the real part of Z is just the real part of Z times the real part of Z. So the real part squared plus the imaginary part of Z times the imaginary part of Z plus the real part of C. So sort of separate these out just a little bit here. You can see the real part squared. Actually, this one here should be minus. It's the real part of Z minus the imaginary part of Z squared plus the real part of C. So that's what I've got here. The next part's easier. The imaginary part of Z is just 2 times the real part of Z times the imaginary part of Z plus the imaginary part of C. And here, it's just this one. So those are the two equations. Once we have that, then it's just a matter of checking our condition. So we need to do the magnitude of a complex number, real part squared plus imaginary part squared. And we just have to ensure, if I go back here, all the way back here, that that does not exceed 4. So while it's less than 4, then we can keep going. While it's great, if it becomes greater than 4, then we're done. All right. So we'll put in here, we'll say real Z times real Z plus imaginary Z times imaginary z. While this value, so this is a magnitude of z squared, while this is less than 4, then we keep going. So as soon as this becomes greater than 4, then we stop. I'm going to say break. And if we make it past this point, then we're going to do it. We're going to increase the number of iterations. So our while loop closes out with this one, with this bracket here. So I'm going to take my matrix, ij, and this is going to equal iteration. So this first little bit here, this is these two lines here. These are iterating the z equals z squared plus c. And then this here is our check, that magnitude squared of z. If that becomes greater than 4, then stop. And then here we're going to save the number of iterations to our matrix at ij. And then after all of this is done, so these are my two sort of ending brackets here for the loops. After I do every single pixel, then I just need to use my image tools dot write image. I'll send in mat, and the file name, I'm just going to call it image dot. We can use a string for this image. We can use a PNG, for instance. That's fine. You can use a JPEG, whatever. It's not a big deal. We'll just write that matrix out to our image. Now, I'm going to warn you right now, we did make a mistake. It's a very, very subtle mistake. If you looked over this and you sort of studied the sort of equations that you need to use and everything, this would look exactly correct. In fact, from a mathematical perspective, this is exactly correct. So we'll run. We shouldn't get any errors. Okay, good. And this should show up. And it's a little funky. Not quite what we're looking for. Seems a little bit off on the, I think this would be closer to the middle, so we might have another sort of issue that I'm not seeing. But I mean, it looks kind of similar, but not quite. So remember what we're looking for here. We're looking for this. So it's got some of the same sort of properties, but not really correct. If you want, you could spend a little time trying to figure it out. It is within the while loop, the issue. So if you want to pause the video and try to figure out where the issue lies, feel free to. But it is within the while loop. These are supposed to be updated at the same time, right? So when we do our z squared plus c, we're sort of artificially splitting it up into a real and imaginary equation, but they should be updated at the same time. But look what's happening. I'm updating the real z, and then I'm using that real z in the second equation. This should still be the old one. This should still be the old real z, not the updated one from above. In other words, it should be this real z that's also used here, not the new one that we just updated. That's the problem. That's the subtle problem here. So we're gonna split this up a little bit more. Instead, I'm going to create a real temp variable. This is going to be a double. And I'm just going to take these two pieces right here. And actually, yeah, we can just take the whole thing. I'm going to put the whole equation in here. The whole equation that we wrote. And I'm going to create another variable called imaginary temp. And I'm going to take this whole equation and put it in here. So now the real z that's used here is the same as the real z that's used here. These two are equal. And then finally, with my real Z and imaginary Z, I'll just set this to the real temp and set this one to the real, to the imaginary temp. So it's just a way for me to get around the fact that I was updating Z and then using it in the same iteration. I don't want to do that. So by creating a little temp variable and doing it that way and then setting them after, I get around that issue. So let's run this again. And it should have updated my image here, and it looks a little squashed. I mentioned that from the other one, so we definitely, I think I probably put in a couple of numbers wrong in one of the places, but it looks basically like what we want. So let's see up here. Yeah, the imaginary start. I had the imaginary start at -2. We don't want that. We want this to start at -1. So -1 to 1, -2 to 1. That's what I wanted. That's why it was a little bit squashed. And there we go. So you can open it. You can change. We can change the resolution. So let's make a higher resolution version of this. You're going to want to keep this at the aspect ratio 3:2, because our start and end is 3:2. 3 in the horizontal, 2 in the vertical. If you change the aspect ratio here to something else, then in order for the image not to look squashed, you would have to change your image resolution. So there is sort of a link between these values and these values. So I'm just going to increase it by, say, a factor of 10. So 9,000 by 6,000 image. That's a very large image. And it's actually going to take a bit of time. It's currently running right now. The larger you make these images, the more time it's going to take to do this calculation. Because think about how many pixels this is using here. This is going through and doing each of these values of C for every single pixel. It's going through and doing up to 255 iterations for each pixel. And there's like 45 million pixels, or 40, was it 40, like 45 million pixels. Is that right? 45 million, 40, 56 million, 54 million, something like that pixels. It's a lot of pixels. So we have a much higher resolution image here than what we just created. And of course, because of that higher resolution image, we get a lot more detail way down in here. Now you still see some fuzziness, of course, because we could go even larger image if we wanted to. But that's the idea here. You can change the resolution. You can change the window. Maybe I want the window to be something smaller. Let's see if we do. Let's say we just wanted this large of an image, but we only wanted to do a smaller piece of it. So let's say we go from like -2 to 0, and then like -0.5 to 0.5. Let's try that. So from here, we're gonna go -2 to 0, and then like we'll do 0.5, -0.5, next -0.5 to 0.5, -2 to 0. So this is a 2 to 1 ratio right now. So if I did this, if I wanted to keep the width to be 9,000, then the height here needs to be 4,500. So it's going to be 2 to 1. And we can run this again. And we should see more detail because we're looking at a smaller region with about the same number of pixels. And hopefully it's not squashed. Hopefully it's sort of on the fly. Hopefully I did that correctly here. So then you can imagine, if you wanted to do this interactively, you could make this into a full sort of JavaFX project and make it so you could like zoom in and it would regenerate it or something at some high resolution. That would be just fine. But again, here we've got tens of millions of pixels that we're messing around with, and it looks like it's finished. So we do this, and it's not quite what I was expecting. There we go, and yeah. So now it's, I thought we had a bit more in here. I guess I was going to 0, so maybe it's not. Maybe I just want to do to like -1. Yeah, so it's good, but maybe I just want to go to be -2. Maybe we just did like a -1. Anyway, this is just something that you go in and play around with here. So now this is -1 to 1. So what we could do is like, you could do like 6,000 by 6,000 or something. that. So this is now 1-to-1 because we have one span and a one span there. And we could run that again. And then I'll show you the colored version of this. So yeah, so that's the idea of the Mandelbrot set. It's not overall, it's not too complicated. And definitely, if you have questions about it, if you're sort of wondering, like, all right, well, how is this, how is this sort of fitting together with the equations that we saw? I can certainly talk more about that, because this is, to me, this stuff, this kind of thing is really cool to be able to generate. So yeah, so now we only go sort of a little ways. Actually, does this get updated? Let me zoom out here. Yeah, there we go. So now we just go sort of a little ways over here, and so we have sort of a higher resolution sort of area in sort of these regions here. So you can sort of imagine making some smaller windows and still using a high resolution to view some of these sort of interesting things that sort of spin off here. All right, if you want to get that colored version, it's a very simple change because I've already added stuff in here. You can comment out the color that's created here, and then uncomment the one that uses the color map. So the color map just looks at the color that you have and actually puts a specific color in there that I've sort of put together. So if we run this now, make sure to save. So it's going to run. And this time, it's not going to just use the raw color from the iteration. The iteration value is going to be taken in, and it's going to be converted into a particular color that I've given to you guys. So now we get something like this. So it makes it so you can see a bit more of the stuff that's going on sort of outside here, which is kind of cool. All right, so hopefully this sort of fractal thing is kind of interesting. There is a very similar setup to do what's known as a Julia set. Maybe I can go over there and show you. It's actually not too bad to do. So it's called the Julia set, and it's basically things like this. So you can do the same thing. It takes a little bit of changing of this code, not very much. You can actually get away with changing probably just 4 or 5 lines, and you can get some cool fractals, basically an infinite number of fractals by changing different values rather than just the Mandelbrot set. So that's something that you can certainly look up. It's based, the Julia sets like this are based off of the Mandelbrot set. Basically, everything is based off the Mandelbrot set to generate these. It's just to sort of give you just sort of a simple rundown here. If I pick one of these pixels in here, particularly one of the ones that's in this sort of border regions, if I pick one of these pixels, I can generate a Julia set based off of that pixel. And so we already do most of the work needed to create a Julia set. It's a matter of picking a C and then going through and iterating over Z with a constant C. It takes a couple of changes, but the loop structure, everything here is exactly the same. It's just dealing with the C and the Z slightly differently. All right, I do this stuff again in the parallel computing class. You notice how long it took to generate that sort of relatively 6,000 by 6,000, a decent resolution image, but it took a little while to do. So in the parallel computing class, I go and we do this again. So if you take me for parallel computing in the future, you will see this again. You'll see probably very similar slides, and we do this on our supercomputer, and so we get some major speed up when we do it on the supercomputer. And there's a lot of cool stuff to think about when it comes to the Mandelbrot set in parallel as well, just for various reasons. So that's basically it. That's what I wanted to show you today. So hopefully you were able to sort of follow along. If you have questions about some of the math, feel free to ask. And if you're interested in potentially some of the Julia set stuff, let me know. I'm more than happy to talk about that stuff. I've had a few students in the parallel computing class go and do the full sort of Julia set treatment of this code as well in parallel, which ends up being quite cool. All right, so that's basically it. So next time, this is the only lecture for this week. There's not going to be 2 because we don't have class on Tuesday. and we're not having in-person classes on either of the days. Hopefully, another interesting topic that'll be kind of fun is some cellular automation. I'll probably talk about it sort of in the first lecture, and then we might actually code it up in the second. We will see. Definitely continue working on your final project. If you have questions about some of the sort of JavaFX stuff, definitely let me know. And we do need to have the second quiz, because I have a few more questions that I have to ask you for various administration reasons. So we'll do a review during the lab this week, and then we will take the quiz on the lab during the lab on the following week. So that's the plan. So the lab the next couple of weeks will be sort of quiz related, and then we'll jump back into some more hopefully useful topics for you guys in the future. So that is it. Hopefully these sort of maybe a little bit more fun, maybe a little bit more mathematical lectures are better than just talking about the JCF for hours and hours. So I will see you guys, I suppose, in lab on this week, and then in person again week after that.